Hi all, so this is question number 32 from GATE 2019, and the question says ask us to and question has given us four statements 1, 2, 3 and 4, and it wants us to find us which of the statements are true. So let's check these statements one by one. So the first statement is that Q denotes the additive group of rational numbers, and f from Q to Q is a non-trivial homomorphism, then it must be an isomorphism. Okay, so let's check whether this statement is true or not. Okay, so solution. First, so f from Q to Q is non-trivial homomorphism okay, so claim, let's write claim in other color, some other color. So claim is that f is determined by f of 1. Okay, if we send 1 to anything, then it will determine the whole homomorphism. And why is that? This is because so f of n, let's take, let n be greater than 0 belongs to integer. Okay, or let for correctness, let be an integer. Then f of n is equal to f of 1 plus 1 plus 1, 1, this is n times, and this by additivity we can write this as f of 1 plus f of 1, f of 1, this n times, and this is equal to n f of 1. If n is less than 0, then n is still an integer, let n less than 0 be an integer, then f of n plus f of minus n is equal to f of 0, which is 0 because it's a group homomorphism. This implies by additivity f of n is plus f of minus n is equal to what? 0. And this means that f of n is equal to minus of f of minus n. And and now because n was less than 0, f minus n is greater than 0. So this will be, and so we can apply this, right? We have derived for n greater than 0, an integer, f of n is n times f of 1. So this will be equal to minus f times minus n times f of 1. This is equal to, okay, n times f of 1. So what do we derive? Therefore f of n is equal to n times f of 1 for all integers n belongs to z. This is clearly true for n is equal to 0. Okay, so for n less than 0 we checked here, and n greater than 0 we checked here. Now let let q is equal to r by s belongs to q. Okay, then what will be f of r can be written as f of s times r by s, and here s is so this is q is a rational number equal to r by s, where it is written in the lowest terms although we don't need lowest term, so yeah, it is whatever. So this can be written as r by s dot 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 r by s, and this is s times, and this by additivity can equal to f of r by s. And now f of r is an integer, so this can be written as r times f of 1. And because s was non-zero, because it's a denominator, so f of r by s can be written as r over s f of 1, or f of q is equal to q times f of 1. So this we have proved that for all rational numbers q, this homomorphism is determined by f of 1. So we have proved our claim. Okay. Now f is non-trivial. So what this means, that f of 1 is non-zero. Because f of 1 was 0, then everything will go to 0. Now we check injectivity. For injectivity, suppose f of q is equal to 0. This means that q times f of 1 is equal to 0. And we are given that f of 1 is non-zero. This means that q is equal to 0. So f is injective. Surjectivity. Given q belongs to q, take q1 is equal to q by f of 1. Now we evaluate f of q1. So f of q1 is equal to f of q by f of 1, and this is equal to f of q by because this is a constant, right? So sorry, and this will be equal to f of q by f of 1 times f of 1, right? Because this is a rational number, q by f of 1. Okay, and this is equal to what I am writing. Sorry. Yeah. So this f of q1 will be equal to q1 times f of 1. And what is q1? q1 is q by f of 1 times f of 1, and this is equal to q. Okay. So we have proven the surjectivity also, and it's given to be a homomorphism, so it's an isomorphism. So the first statement is true. Okay. What about the second statement? So it says that any quotient or group of a cyclic group is cyclic. So second statement, let G be a cyclic group, then G can be written as generator. It is generated by something. Let H be a subgroup of G, then G modulo H is equal to what? It will be generated by the coset G plus H. Right? So G modulo H is cyclic. So the second statement is also true. What about the third statement? So third statement says that if every subgroup of a group G is a normal subgroup, then G is abelian. If you know this, then you know the answer. Otherwise, like, it's very hard to guess whether this statement is true or false. It seems like a very true statement, but in fact it is a false statement. So the counter example of this statement is given by the quaternion group Q8. Okay, so let me write third statement is false. So the quaternion group Q8 is generated by ijk, and ijk satisfies relation I square is equal to j square is equal to k square is equal to ijk is equal to -1. Okay, this is the quaternion group, and it has following lattice of subgroups. So it has 3 subgroups of order 4. These are generated by I, J, and K. It has this is the center, plus and -1 are center of this thing, and it has this trivial subgroup. Okay, so these are all the subgroups of this quaternion group. You can check that, and this trivial group is of course normal in the whole group, and the whole group also is normal in the in itself. And this group plus and -1 commutes with everything. -1 commutes with everything. It's just the normal -1. So in fact this is the so it is in the centralizer of this Q8, center of this Q8. So this is normal. Any subgroup of center is normal. Now these three groups are of order 4, and why these are normal? So fact, any subgroup of index 4 is normal in the group. Sorry, any subgroup of index 2 is normal in the group. Okay. So yeah, this is no so this is of order 4. So this is of index 2 here. This is of index 2. This is of index 2. So these 3 subgroups are also normal. So you see that all the subgroups of this group Q8 are normal, but Q8 is non-abelian. Why is that? So ij is equal to k and ji is equal to -k. So, and k and -k are different. Okay, so this is false. So this is false. What about statement 4? False. What about statement 4? Every group of order 33 is cyclic. Well, let's see that. So you must have seen this fact for every group of order PQ is cyclic if P doesn't divide Q minus 1, where Q is greater than P. This is a fact. You must have seen it. So the result is immediate from here, right? What does it say? That we have group of order 33 which is written as 3 times 11, and 3 doesn't divide 11 minus 1, which is 10. So every group of order 33 is cyclic. Okay, so fourth statement is true. And what is the correct option? So the correct option is C option, first, second and fourth. So thanks.